Welcome to this fourth video in the Part A lecture notebook in the fourth module on computational applications. This is on root finding, and in this video we will discuss expanding the bisection class and not the plot tools for roots class. Specifically, we'll expand the bisection class to include this useful plotting function, referring to the plotting function plot bisection that was shown above, that enhances our visual storytelling of the bisection algorithm in the root finding method. For instance, if we increase n and we run interact, we get some more annotations that describe what the approximate root is following 6 steps of the bisection algorithm in this case, as opposed to 1. So it just allows us to improve, enhance our visual storytelling elements, the visual narrative that we are conveying to the user with these plots. Now you might ask, why do we want to put such a plotting tool inside the bisection class and not in the plot tools for roots class? Well, the plotting function we are interested in coding fundamentally relies upon the outputs of the bisection algorithm. It is in fact the first step in this function. If you scroll up, and I apologize for that, if we look at this plot bisection function again, which was discussed in the third video, we see that the first step is to compute the bisection algorithm. And then everything else was about adding annotations to the plot related to the number of steps in the final root approximation from the compute bisection process. So when we come back down and we think, where should we put this information, this type of method attribute inside of our classes? Well, it belongs in the bisection class more than the plot tools for roots class, at least arguably so, because it relies upon the bisection class acting first, or at least acting in some capacity before we even have enough information to add this information to our plots. So in doing this, we are going to expand and make the bisection class look quite a bit larger. One suggested activity is to add doc strings and code comments below for you to do as a student. Another thing you might consider doing, it's not on here, is to subclass the bisection object into a subclass maybe called bisection visualization. So you might think of bisection visuals, and then maybe you subclass this from the bisection class, right? And then you wouldn't need perhaps any of these other methods because they would be in the original bisection class, and you would just have this new method that was involving the plotting of the bisection and its annotation that was coming from the plots. So that's a good thing to try to do, is create a new one, just in the interest of keeping everything there so you can see how all the pieces fit together. I'm just creating a larger and larger class with the bisection class having these plotting elements in it. But again, make this your own. Play around with it. Doing a subclassing of this is a really good idea, in fact. You kind of have your basic bisection object class template that describes everything that you need for bisection, and then you consider subclassing it based on other ways in which you might want to incorporate other elements of the visual storytelling, or perhaps even other enhancements to the algorithm in some sort of subclassed features. That's up to you. I recommend trying it out, though. I think you'd really learn a lot by going through and doing that. But in the end, the only thing that's changing here are these final two methods, plot bisection and plot bisection annotate. So this is the same basic structure as what we saw before for the plot bisection function, but I've modularized it. You'll notice that when I call the plot bisection, that in doing this, you will set A, B, and N if any of them have been updated. So perhaps these have been called elsewhere. Perhaps you have actually set the bisection parameters, you've computed the bisection, and then you just call plot bisection. Notice one of the things that we were doing when we computed the bisection was we created these new data attributes, self.an, self.bn. These were the final A and B values of the interval that we bisected after n iterations of the method. So if we've already run this, because we already set A and B values and N values, then we would call the plot bisection with just the range of X values for the plotting, maybe changing how many points we want to plot of the function, and maybe determining whether or not we want to show the final interval. But we already have all the information we need for our plotting what the result is of that bisection algorithm. So we would maybe leave everything as default, including A, B, and N as none. And it's not because they're actually none in terms of attributes. They would have already been set here. We would have already called this in order to compute the bisection. And then when we're calling this and they're none, we would go set these parameters, and it would just see, oh, well, you passed A and B and N as none, and then it wouldn't overwrite what these values are because it only does this if A, B, and N are not none. So as far as this plot goes, it just allows you to, if you have an A, B, and N in mind and you just want to see how it would perform, you can call the plot bisection with those A, B, and N values. It will then set the bisection parameters. It will then compute the bisection algorithm. And here, there's a little bit of redundancy, I'll admit, that if A and B and N haven't been set before and the compute bisection's already been called, it's just being called again, in which case it's redoing these results and the values will be the same. Oh well, you could get a little bit more fancy here. Perhaps if A, B, and N are already none, maybe you just skip this step because that means that you're not trying to plot anything that you haven't already computed. And then we use the plot tool data attribute, which you'll remember is calling the plot tools for roots class, right? So it's made this as an object. This data attribute is itself an object, and it has some basic plotting utilities in there. So we actually plot the function based on this, and then we also plot the annotation for the bisection algorithm. And this is just, if you go look at this plot bisection function, this is exactly what was done before here with the plot bisection. We go through and we plot the function, and then we do a bunch of annotations that are following it. And these annotations are based on whether or not we're showing the final interval on top of everything else. So it looks like a lot of code here. It's around 50 or so lines of code for this plotting and the annotation. But a lot of it's just types of code we've seen before, like scatter plots, annotate plots, scatter and annotate. And it's just if the final interval is supposed to be shown or not. And then a scatter plot of the final value, the root approximation, and annotating that in ways we've seen before using the dictionaries for arrow props and everything. And I come back down here now. I've just modularized that plot bisection annotation, and that just comes in here. So there's a certain amount of annotation that can potentially come in here, although I'm saying show root is false. And then I am annotating everything here. And this looks, if you look at it, whether or not I show the final interval and what annotation I'm doing, it's going to look a lot like what we saw in the plot bisection algorithm, except I'm rewriting certain hard-coded elements or things that were passed to that function in terms of A and B into the data attributes of this object. So it's like self.b, self.f. But otherwise, it's effectively the same code. So there's actually not too much to say about it. I'm not going to dwell over the code because it's a pretty straightforward modification of the method we saw before, but just bringing it in as a method inside of a class so that self is the first argument. And then there's basically these parameters, these data attributes that are being called within the various plotting functions. So when we run that and then we create this bisection class is now improved. Once I've run this code cell, this is the new template for the bisection class. And so now when I set some bisection parameters, again with our standard x cubed minus x minus 2, and I look at plotting our function, look what happens now. Well, I went to call it. I never called compute bisection. I just set bisection parameters and then I immediately said plot the bisection. So this is for n equals 10 with a and b being -1 and 3 respectively. And recall, in this class, again, in the method in this class, when you call plot bisection, it will compute the bisection. It could possibly be redundant if I've already computed it before, but it will compute it, get all of these data attributes it needs, and then it will go and create the plot information with the annotations. And so this is kind of nice because it's a one command basically. Set the bisection parameters, now plot, or in the plot bisection, I could have also passed these parameters as part of it. And here's our nice annotated plot. Here's where our initial A and B are. Here's our final root approximation after 10 steps of the bisection algorithm. So that's a nice kind of visual storytelling of what the bisection algorithm did based on where it started with an A and B that bracketed the root. So you can also do this with a widget. I'll just go ahead and show the interaction. Notice to do this with a widget, the method I'm calling is plot bisection within the bisect object. So you need to have instantiated this object first, and then this is how you would use a widget for it. f_bisect dot plot bisection. This is a little different than what we had before, where we had a plot bisection function, and we were just interacting with that function directly. Here it's slightly different in that we've create this method, this function is part of this class, and we just then call that method within the class. That's it. But now I'm not passing the function as an argument, but I am passing a, b, and n. So when I run interact on here, again, I'm showing a and b is 0.5, and what would this be? It's kind of hard to see. The plot's a little crowded here, and so that might be where you'd say, boy, that x min and x max, maybe if I'm choosing a and b there, and I wanted to maybe make the x min and x max equal to, what was that, 1.75 for b. There we go. Now let's run interact. That looks a little better. That's one step, right? One step of the bisection algorithm is not great. It bisects it right in the middle. We clearly need a few more iterations of the method. And at 5 iterations, it's over there. And where is it at 9? At 9, it's over there. And you'll notice I'm not cluttering the plot with all the information at other end, like what was happening in my plot bisection function. The reason for that is if we come in here and we look at what's going on with the plotting, when we call this plot tool right here, which is what we call the plot function within that plot tool, and we come back up and we look just to remind ourselves what was going on in that plot function. So it's a lot of scrolling. I know it's kind of a long notebook because there's a lot of information in here. When we plot this, here we go, we clear the figure as a default option so that every time we do the plot, we don't clutter it, because we're noticing in some of our steps, some of our code examples that we have, for instance, if I come down here, this starts to get a little cluttered, right? I could, let me rerun this. There we go. Run it again. If I start adding this information, by varying in and running the interact, you just see like everything's getting very cluttered and it's hard to see what's going on. And so in the class, one of the things that I did in the method for the plotting tools for roots was to clear the figures in anticipation of wanting to not have cluttered plots that are annotated so that it has a clearer story tell. You can also see the advantage of the alpha value being set to 0.5 in that it creates enough transparency to not to allow you to see where this point b, f of b, is described. That annotated box right there is not hidden by this box. If I made the alpha 1 so that there was no transparency, this would have been completely hidden. And again, that alpha value, that was something discussed more in a previous video, but just to show you what this is in the plot tools, I will come all the way back up here. And this is in the box. Here we go. The alpha values here are 0.5, 0.5, 0.5. It's all the same. If I made that 1, there would be no transparency. 0.5, there's a decent amount of transparency to where you get, again, looking at it, a pretty nice, sorry for all the scrolling, a pretty nice looking box. You can see everything in here, and you can see that BFFB. So again, that was a design choice I made because sometimes these boxes can overlap. And in that case, you're going to want to use some transparency generally so that you can see the things underneath. I mean, you don't have to, but again, it's a design choice. So that was, I chose X min and X max there. I'll go back to the original values, -3 and 1, and just rerun this. And you can see kind of how crowded that gets there. And you can play with the A and B values to also uncrowd it a little bit. So there's some bracketing of the root. There's your 1 approximation. Play with the N. But you can play with this, again, on your own. Try subclassing, add doc strings and comments, do all of these various things. That's pretty much it for this video. I will also have a solution video about this activity playing with the bisection algorithm. That will be posted on Canvas, not embedded in here. Thank you for listening.